Welcome to the Explainer. Let's jump right in. Because today we're unpacking a major software release from June 26, 2026 that directly targets a massive structural problem in computational neuroscience. We are decoding NeuroByte version 5.2.0. Now, this isn't just some minor software update. It's a powerful algorithm specifically designed to finally standardize brainwave analysis and, frankly, bring some desperately needed order to a very chaotic field. I really want you to think about this for a second. How do we actually ensure brainwave research is reproducible? You know, science broadly has been grappling with a severe reproducibility crisis. Just think about it. If two independent labs study the exact same brain phenomena, but they process their raw data just slightly differently, they can end up with completely contradictory results. It's incredibly frustrating for researchers. So what's the fix? Identical, airtight preprocessing across the board. And that is exactly the giant puzzle NeuroByte aims to solve.
Okay, let's dive into this. We are breaking this complex code into 5 easily digestible pieces. Number 1, we'll meet the NeuroByte algorithm. 2, we'll trace the BID's data journey. 3, detecting neural events. 4, generating the timing fingerprint. And finally, number 5, standardizing the future.
All right, kicking things off with part 1. Meet the NeuroByte algorithm. Let's build the foundation of what this tool fundamentally represents.
Let's look at the technical definition. NeuroByte version 5.2.0 is a standardized Python and MNE framework designed to extract candidate transient neural timing events from BIDS-compatible EEG recordings. Okay, stripping away the heavy jargon, what this really means is that NeuroByte acts as the ultimate bridge. In the past, researchers usually had to build their own custom, handcrafted data pipelines just to get from raw data to a finished result, which, as you can imagine, directly fueled that reproducibility crisis we were just talking about. Now, this framework takes all the guesswork out of the steps in between. On one side, you have your raw brainwave data, perfectly formatted to the BIDS standard. And on the other side, you get perfectly reproducible, mathematically sound research.
Let's move into part 2, the BIDS data journey. How does a raw dataset actually travel through this thing? Well, the absolute brilliance here is that NeuroByte doesn't try to reinvent the wheel. It's built entirely on familiar, widely used foundations. You definitely don't need access to a multi-million-dollar proprietary supercomputer to run this. It relies on standard, highly accessible Python libraries. A simple command in your terminal, literally just pip install MNI, MNI-vids, NumPy, SciPy, and Pandas, gets the entire environment up and running. It's pretty amazing when you think about it. That single line of code means any researcher, sitting at almost any laptop anywhere in the world, can easily install and execute this advanced processing pipeline.
Let's move to and see how this builds into the actual pre-processing pipeline. I want you to imagine your raw, messy data entering this system. First, it hits step 1, where it gets cleaned up by a band-pass filter, isolating frequencies right between 1 and 30 Hz, basically stripping out irrelevant noise. Then, moving to step 2, the algorithm calculates the Hilbert envelope to mathematically trace the actual power of the signal. In step 3, it applies z-score normalization to standardize the scale across all different subjects and recordings. Once the data is beautifully prepped and standardized, we hit the true magic in step 4, the NeuroByte event detection phase. That curated data feeds right into step 5, feature extraction, ultimately stamping the data in step 6 with a final, highly precise timing fingerprint.
All right, part 3, detecting neural events. We're zooming in on step 4 of that pipeline now, because this is where the real analytical heavy lifting happens.
Now, what's really interesting about this slide is this single highly important number, 2. Within the algorithm's detection phase, a neural event is only triggered when the z-scored envelope hits 2 or more standard deviations above the baseline. Basically, the software is constantly scanning for significant amplitude excursions in the brainwave. If the neural signal doesn't hit that magic number 2, the algorithm simply ignores it and keeps looking. It is a hard mathematical floor.
But here is the catch. Hitting that amplitude threshold isn't enough on its own. Enter the 50 to 100 millisecond rule. This acts as an incredibly strict duration gateway. The algorithm demands that the signal must remain above that 2 standard deviation threshold for a minimum of 50 to 100 milliseconds continuously. Why? Well, to prove beyond a shadow of a doubt that it's an actual biological neural event, not just a random spike, an eye blink, or some quick glitch in the hardware. This brilliantly illustrates the exact difference between a genuine scientific finding and mere electrical noise. On the left, we've got valid neural events. These are the gold standard signals that successfully sustain the amplitude threshold for the minimum duration, while also perfectly respecting the necessary refractory periods, the quiet times between events. Now contrast that with the right side. Here we have spurious artifacts. These are the signals that fall below the threshold way too quickly, or maybe they hit optional upper exclusion thresholds that are specifically designed to catch things like jaw clenching or muscle artifacts. By seeing these outcomes side by side, it's crystal clear why having these strict computational criteria is absolutely essential for filtering out the overwhelming background noise of the human brain.
Moving to part 4, generating the timing fingerprint. The data's been filtered, events are detected. What actually comes out the other side?
Once the pipeline finishes its run, the algorithm outputs 4 beautifully organized BIDS-compatible derivative files. You get neurobyte_events.tsv, neurobyte_metrics.tsv, timingfingerprint.tsv, and a neurobyte_metadata.json file. Now, you might be thinking, okay, great, just more text files. But for researchers, having these formatted right out of the box as BIDS derivatives is an absolute lifesaver. It literally saves hundreds of hours of tedious manual data formatting. Because they're already standardized, they are incredibly easy to integrate directly into massive open neurodata sets and existing MNE Python analysis tools without changing a single line of code.
Let's look closely at what's actually computed inside those files to summarize the brain's activity. The software groups these metrics intelligently to build a comprehensive profile. For core counts, it calculates the raw event count and the overall event density over time. It deeply analyzes duration, specifically tracking the mean event duration. It also meticulously measures the intervals between these events, tracking the mean inter-event interval alongside its standard deviation and coefficient of variation. Finally, it scores the overall reliability of the signal with a distinct stability index. All of these nuanced metrics mathematically combine to create that precise, singular timing fingerprint that's completely unique to that specific recording.
And that brings us to part 5, standardizing the future. Let's pull back and look at why this really matters.
The transformative power of this level of standardization simply cannot be overstated. Because NeuroByte provides a truly common mathematical framework, it finally enables cross-cohort comparisons. This means completely independent research groups in entirely different countries can finally compare apples to apples. Not only that, but it significantly facilitates accurate test-retest analyses, allowing labs to confidently verify their own previous findings. Furthermore, it empowers independent replication studies at a scale we haven't easily seen before. Add in the seamless integration with major open science platforms, and you've got a tool that takes isolated, fragmented, messy data and brilliantly turns it into a unified, shared scientific language. So, the crucial point is this explicit disclaimer straight from the source. We have to be very clear about what this software is and what it's not. It definitively states, the software is not a validated clinical diagnostic tool, and any potential biomarker applications require independent replication, external validation, and regulatory evaluation before clinical use. This strictly delineates NeuroByte as research use only. It is deeply important in neuroscience to clearly distinguish a computational software implementation from any future clinical or medical claims. Establishing this boundary ensures total scientific transparency and responsibility. Which brings us to our final thought for today. With elegant algorithms like NeuroByte finally creating a rigorous, common language for EEG data, what incredible breakthroughs will independent, standardized replication unlock next in neuroscience? Now that researchers across the globe can finally speak the exact same data language, the possibilities to decode the human brain are truly endless. Thank you so much for joining me for this explainer. Keep questioning, keep learning, and definitely keep exploring the power of standardized neuroscience frameworks.